There are some higher level safety engineering challenges which have to do with understanding the difference between, yeah, it kind of seems to work, and no, really, this will be safe at scale. The first one is that you have to understand only the bad days matter. Let me make that really concrete with a hypothetical example. Let's say that you have 99,999,999 safe miles out of 100 million. Now in the US, it's ballpark 1 fatality per 100 million miles, depending on the year, depending on a lot of specifics, but it's about 1 fatality per 100 million miles, which means all but one of those 100 million miles was a safe mile. Nobody died. Sure, there can be other crashes. Let's set that aside. Let's say you have that ending in 999 versus that ending in 998. Well, those numbers look almost the same. And so if you're saying, well, we're worried about it performing well, those numbers are basically the same. But safety can't look at it that way. Safety has to look at, well, you had 1 fatality per 100 million miles. We had 2 fatalities per 100 million miles. That's a factor of 2 safety difference. So the thing is that only the bad things matter for safety because you're expected to almost never have a fatality. So a number that seems almost the same with a very small change can actually be a dramatic change in unsafe miles, which are the things that matter. In this context, a single 10-mile safe drive means essentially nothing. Oh, I drove 10 miles and everything was perfect, must be safe. Well, 99,999,990 miles to go, and even then your confidence is kind of low. The second big problem with safety engineering is that because rare high severity events dominate the safety discussion, you have this struggle with zero probability times infinite cost. If something almost never happens, well, 1 per 100 million is almost never, it's very rare, but it does happen. What if you have near zero probability and a catastrophic consequence? Remember the question marks I put in low frequency, high severity? Well, what do you do with that box? Economics pressures you to say, well, it's never going to happen, so we're going to assign it a low CIL because there's less engineering rigor, less redundancy, it's a cheaper product to make, easier to make. So it's probably not going to happen, so we're not going to worry about safety. Economics pushes you that way. News headlines push you the other way, because once the bad thing happens, you say, wait a minute, that horrible thing happened. We should have guarded against it, even though it was extremely rare. What you see is these philosophy for rare high severity events varies depending on the application domain. Automotive tends to make these rare high severity events low risk, low CIL, and aerospace tends to make them high CIL. In the robotaxi business, there's a lot of incentive to not worry about rare events. In fact, companies will say, well, that's a rare event, so it shouldn't count. And that works until the company has a really severe event that makes the news and causes loss of confidence. And ultimately, many companies have been put out of business by having a single high severity event. One of them was Cruise, which went out of the robotaxi business after they dragged a pedestrian down the road. And of note here is that it was a horrific crash, but it was a severe injury. It was not a fatality. And yet that and some associated circumstances were enough to take them off the market. So you can talk yourself into low CIL for rare events, but it has a way of catching up with your company if you do that.